Hello. Okay, so then now let's think about the second example, gas price in New York City. Uh, the population to answer this as the population in this example is all gas stations in New York City, right? If you can visit all gas stations, it's not a statistical inference anymore. It's simple computation, but you cannot visit all gas stations in New York City. Instead, you randomly choose a few gas stations and say call them and ask their gas price. You can do it for say 100 gas stations. I don't know how many, but anyhow, say a certain number of gas stations can be chosen at random and uh, uh, get their gas price. That will be your sample. And also from based on those population and sample, I will define the parameter, the what we want to know, as is the mean gas price of all gas stations in New York City. So it is mean about the population, therefore it is a parameter. This is what you want to know. And a statistic I'm going to use is the mean gas price from the sample. So you observe just a finite number of gas prices, calculate their mean, you can calculate their average. That is your statistic. That is your estimator. So the statistic is calculated from the sample. So um, so this structure is very important to understand because later what we are going to do in the end in this chapter and the later chapters is to study the relationship between parameter and statistic, the population and the sample. So we would like, for example, we'd like to study how accurate the statistic is about the parameter, right? So here I will give you a warm-up question. So for example, here's another example. We would like to inspect some batteries from a shipment to check the defect rate. So you are say a smartphone or electric car maker, and you get shipments of batteries from another company, another factory. So when you receive them, you'd like to see if they are okay or not. So you inspect some randomly chosen batteries and see if they are fine or if they are working or not. So this inspection is another kind of statistical inference in some sense. So then what is not correct? First, the population is all batteries. Two, sample is the inspected batteries. And C, the parameter is the probability of defective batteries among all batteries. For statistic is the probability of defective batteries among the inspected. And finally, nothing is incorrect. Everything is correct. Guess, think about this, right? The answer is E. All these four are correct. So when you inspect the batteries, what you want to know is the parameter, the probability of defective batteries among all the batteries. But you cannot test all of them, so you only choose a finite number of batteries and inspect them. That is the sample, and you calculate the probability of defective batteries among the sample, which is your statistic. So this is another example which has the same structure as statistical inference. Okay. Now the next, what we are going from now on, what we are going to do is to set up some basic understanding of about the parameter. So when I explain the parameter is a target, then it's about the population, then it sounds obvious, but actually it's not. So it's very confusing concept. So I would like to have a few more minutes slides explaining the parameter. So here are 5 examples. So assume like this, like you'd like to estimate something. Then your something, the target, one of them cannot be the target. So guess what is not a parameter? So you are estimating something, and the something should be a parameter. Then what is not a parameter here? Standard deviation of life expectancy. Like, so someone lives longer and someone die early, and then what is a standard deviation? And expected increase in sales after a price cut, and total number of heads when tossing 10 coins, and difference in mean gas prices in New York and California, conditional probability of making a second free throw after making the first in basketball. So if you'd like to estimate these 5 things, one is not working. One you cannot estimate. What is that? Guess. The answer is C. The total number of heads when tossing 10 coins is random. Even if you throw the 10 coins, repeat that experiment for an infinite number of times, still the number of heads is random. You cannot, it's random, forever random, right? So it cannot be a target. You have to set a target and you are estimating that. But when I say I'd like to estimate the number of heads, does not make any sense because it's random by nature. On the other hand, all the other 4 examples are well-defined parameter. And because if you know everything in like hypothetically, if you can observe an infinite number of observations, for example, if you know everyone's life, then you can calculate this. And if you can repeat this experiment for an infinite number of times, like so price cut is an experiment. If you can repeat that like infinite number of times, you can calculate the increase, average increase, and difference in mean gas prices. If you can visit all the gas stations, you can calculate that. Free throw, making the second free throw after making the first. So if you can shoot a free throw for an infinite number of times, then you can calculate that probability. So all the other guys are just matter of whether you know the population or not. So if you know the population, the other 4 can be calculated. However, as I said, C is not. So even if you toss coins for an infinite number of times, the number of heads will be different all the time. So C is not a good parameter, not a parameter, cannot be a parameter. So then what we learned is that for something to be a parameter, so that means for something to be the target of statistical inference, it must be non-random, right? And it should be calculated. You should be able to calculate it if you can repeat the experiment for an infinite number of times, right? It's obvious, but it's confusing without this. Like so, this example will help you understand what I meant by the parameter. So now, okay, then parameter is relatively easy. It's clear, right? And then the next step is to think about the estimator. You already suppose that you set the parameter, so you know what you are estimating. And suppose you would like to estimate the expectation of a random variable x, right? It's the expected value of x, and then it's like a question. What is the expected value of x? Then, as a statistician, you have to answer that. Statistical inference is to answer that kind of question, and then your answer may be like accurate or maybe wrong, but like without considering if it's good or bad, there can be a lot of possible answers, right? So for example, you may use the sample mean, or you may use the sample mean after deleting the minimum and the maximum, like in the Olympics, like calculating the mean after deleting two extreme values. Or you may use the sample median, right? So some may be better than the others, but all of them can be an answer, right? Even if they are wrong, still not a problem. So still they can serve as an estimator. So an estimator is a statistic to estimate a parameter, right? It's obvious. But what I want to tell you here is, before studying what is a good estimator, first we have to think about what cannot be an estimator. Like we considered what cannot be a parameter. So let's think about this. You want to estimate the mean gas price in New York City using 100 observed gas stations. So you have 100 observations about gas prices. And then, think about this. Which one you cannot use as an estimator to estimate the mean gas price? So most of them may be wrong. Most of them sound totally wrong. But I don't care. At this point, there is one that simply cannot be an estimator. So first, any number that came to your mind, such as like say $10, whatever number you see, like if you see the watch, the clock, what time is it? Use that number, any number. B, half of the sample average, so X bar divided by 2. And C, the sample variance calculated from 100 data. And D, the population mean. E, the gas price at the nearest gas station, whatever, or the first gas station you called. So there are five objects, which most of them are absurd, but one is not an estimator at all, cannot be an estimator at all. What do you think? The answer is D, population mean, because it is unknown. You do not know the population. That's why we are doing statistical inference. So population mean is not calculated, cannot be calculated. So you cannot use that as your tool. It is not available, right? And actually, this is a parameter. It can be a parameter, but cannot be an estimator. However, the other guys, any number came to you. So it's like this. So when I ask you, what is the mean gas price in New York City? Then you have to answer something. The something should be a number. And list should be a number, a concrete number. Say like $10, $100. It's absurd, but still it is an answer. Just it is wrong. However, the population mean is not a number because you don't know. You don't know what it is. It is, so when I ask you what is the mean, then you're answering mean. So when I'm asking you what's your name, then you have to say something, whatever, but you cannot say my name is my name. That is not an answer. That cannot be an answer. So it's like that. Population mean is unknown. So and the other guys like this or taking half makes no sense, but still they are estimators. They can serve as an estimator, right? So I showed you an absurd example to give you a simple idea what cannot be an estimator. So we learned what cannot be a parameter, what cannot be an estimator. It's important to to get an idea of what we are doing and the relationship between an estimator and a parameter. And then the natural question for the next step is then, okay, there can be a lot of possible estimators. Then what are good estimators? So the ultimate goal is to find a good estimator. So we are going to answer that question. What is a good estimator? And we are going to develop two criteria for an estimator to be good. Okay, we will study that in the next video. It will be the main part of this chapter. See you later.